In this lecture, we're going to start chapter 4, which is exponential and logarithmic functions. 4.1 is an introduction to exponential functions. I'm going to start with the definition of the exponential function. So the exponential function f with base b could be defined by f of x equals b to the x. Or we could write it as y equals b to the x. Remember, y is equal to f of x. B is a positive constant other than 1. So b is greater than 0 and b can't be equal to 1. Otherwise, f of x would just be equal to 1 and we'd have a constant function, a linear function. And x could be any real number. So here are some examples of exponential functions. F of x equals 2 to the x is an exponential function with base 2. G of x, and let me make this a little bit bigger. G of x equals 10 to the x is an exponential function with base 10. H of x equals 3 to the x plus 1 is exponential with base 3. And j of x equal to 1/2 raised to the x minus 1 is also an example of an exponential function, and its base is a half. So let's just practice evaluating exponential expressions. So A, we're going to evaluate 2 to the 3.4. B will evaluate 4 raised to the negative 1.5. And C will evaluate 5 raised to the square root of 3. So we're just going to plug these in the calculator. So I'm going to screen share my calculator, and let's just practice using our exponent key in the calculator. Okay, so the first one was base 2, right? And then anytime we want to raise to an exponent, we're going to use our exponent key, which is right above the division key. And now we could type in the exponent, which was 3.4. Enter, we get 10.556. Let me just go back and see what we were rounding to. So it didn't say where to round, so let's just go 2 places. So it's going to be about 10.56 if we go 2 places. So to 2 decimal places, that's about 10.56. Next, let's evaluate 4 raised to the negative 1.5 power. So 4 raised, right, my exponent key. And then to the negative, make sure you're using your negative key, 1.5. And to 2 decimal places, we get about 0.13. So 0.125 will round to about 0.13. And we'll do one more. Let's do 5 raised to the square root of 3. So base 5 raised to, and now pull up our square root, right? And we're going to put 3. So 5 raised to the square root of 3 to 2 decimal places is about 16.24. So example 2 is still going to be more practice evaluating just an exponential expression, but now it's going to be in context, so in the form of a word problem. So in example 2, it says the exponential function f of x equals 42.2 times 1.56 to the x models the average amount spent f of x in dollars at a shopping mall after x hours. So this function is modeling the amount of money spent as a function of time. So how long you're at the mall in hours. So the question is, what's the average amount spent to the nearest dollar after 3 hours at a shopping mall? So X is the shopping time, right? So basically, when X equals 3, what's the value of the function? So we want to evaluate the function at 3 hours. So we're going to input 3 into the model, right? So we're going to get 42.2 times 1.56, and we're going to replace x with 3. And this we could plug into the calculator as well. So we have 42.2 times 1.56, and now we have to raise that to the third. And it says go to the nearest dollar, so it's about $160.21, but if we round that to the nearest dollar, it's about $160. So this is going to be approximately $160 after 3 hours at the shopping mall. So really, these first two examples are just practice evaluating an exponential expression. So now let's think about what an exponential function looks like. So for example, let's graph 3 to the x. So what if my function y, because remember, f of x is the same thing as y, what if that was equal to base 3 to the x power? So that's an example of an exponential equation or function. What does it look like, though, graphically? So we can make a table of values to get some points to plot this. So that's what I did down here. So I made a table where we could pick some x values, and then we could evaluate the y values given those x values that we picked. So let's think about this. We said up here that when we're dealing with an exponential function, x can be any real number. So I can take base b and raise it to any power that I want, whether it's in terms of being a real number. It could be positive, it could be negative, it could be a fraction. So let's pick some values for x and then we'll plot it. So for example, what if x was equal to -2? What would y be equal to? So let's plug in -2 into my function. So f of -2 is going to be 3 raised to the -2, which is, remember, 1 over 3 to the +2, or 1/9. So it's a tiny number. Now, why don't we pick 0? What if x was 0? Then f of 0 would be equal to 3 to the 0. Remember, anything to the 0 power is 1. What if x was 1? Then f of 1 would be equal to 3 to the first power, which is 3. And let's pick another value of x. Let's pick 2. So f of 2 would be equal to 3 to the second power, which is 9. So now I have 4 ordered pairs that I could plot, right? So here we have -2 1/9, 0 1, 1 3, and 2 9. So -2 1/9. So 1/9 is like if I were from 0 to 1, if I were to divide that scale into ninths. So it's going to be very, very, very close to 0. So I'm going to go over 2 and then barely up on the y, up 1/9. So we're barely moving up the y-axis. Then I'm going to have the point 0 1. Then I'm going to have the point 1 3. And then we have the point 2 9, which is going to live up here, right? So we have 5 6 7 8 9. Let's say it's about here. And my function is going to look like this. So we have an increasing function, and the graph is never going to touch the x-axis. It's going to get closer and closer and closer and closer to the x-axis, but it's never going to touch it. And the reason is because y can never be 0. And I want you to see something. Like, we're doing my function's 3 to the x, right? Let's make x a really, really negative number. So what if I had, I'm sharing my calculator now, 3 raised to the negative 1,000. It's going to be very, 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 very close to 0. But not exactly 0. So the calculator is telling us, okay, it's going to be approximately 0. And the reason is it can't fit all the zeros on the screen. So really what we're doing is this is like 1 divided by 3 to the 1,000th power. So it's going to be a very, 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 very tiny number that's going to get closer and closer and closer to 0. But the graph is never going to touch the x-axis. So let's talk about some properties of this graph. So let's think about domain and range. So in general, if I have f of x is equal to some base b to the x power, like in this case here, my base was 3, right? The domain is going to be all real numbers. And we said the range is going to go from 0 to infinity, right? Because this graph is never actually going to touch the x-axis. So x could be anything, all real numbers, but y is strictly greater than 0, or 0 to infinity. And the graphs of all exponential functions in the form f of x equals b to the x are going to go through the point 0, 1. And that's because b to the 0, right, doesn't matter what the base is. Whatever the base is, whether it's 3 or 4 or 5 or negative 6, if I raise it to the 0 power, it's going to be 1. The graph is increasing. So as we go from left to right, it's an increasing function. And the greater the base, the steeper the increase. Now, an exponential function can be decreasing. If b, the base, is between 0 and 1, so if it were a fraction, then the graph would be decreasing from left to right. So the smaller the value of b, the steeper the decrease. And we said that the graph of b to the x approaches but does not touch the x-axis. So let's look at let's go back to the calculator for a minute. So let's graph 3 to the x, just so we could see it, more to scale. I know I did that by hand and we were estimating where 1/9 is, but let's make a really nice graph here where we can see it to scale. So let's do 3 to the x, and then we'll graph it. And we could see that increasing function. And it almost looks like it starts right to the left of x equals 0. But since the graph gets closer and closer and closer and closer to the x-axis without touching it, on the graphing calculator, it's just very hard to see the graph. But the graph does come in from the left, from negative infinity. Now what I want to do on the same graph is, now let's make b a value between 0 and 1. Let's make it a half. So let's make it a fraction, the base. So what if we took 1/2 and raised it to the x power? Now my graph is going to be decreasing. You see how it's decreasing from left to right? But now the thing that I want to point out, even though one graph was increasing, the other graph is decreasing, look at where they both cross. They both have a y-intercept of 0, 1, which is what I was explaining before. So regardless of b, when we raise b to the 0 power, that's going to be equal to 1. So all the graphs in the form y equals b to the x are going to go through the point 0, 1. So that's what an exponential function would look like in terms of a graph. Our properties for transformations, if we apply them to exponential functions, they're still the same as when, we did it previously. Whether we were transforming x squared, square root of x, absolute value, the rules are still the same. So if we were to add or subtract a constant from b to the x, it's going to be a vertical shift up or down. If we were to make an inside change and add or subtract a constant from x, that's going to be a horizontal shift, left or right. If we were to negate the function, remember that's a reflection about the x-axis. And if we were to negate x, that's going to be a reflection about the y-axis. And if we multiply the function by a factor of c, that's going to be a vertical stretch or compression, depending on what c is. And then if we multiply x by a factor of c, that's going to be a horizontal stretch or compression. So same rules apply as to when, we learned this a couple of chapters ago or a couple of sections ago. So actually, before we get to the base E, let me show you an example in the calculator. So let's say we have y equals 2 to the x. But now let's also graph 2 to the x and then plus 3. So 2 to the x plus 3 should be the graph of 2 to the x, but shifted vertically 3 units upwards, right? So there's 2 to the x. And now the second graph, which has increased by 3 units, right? Now it's going to go through the point 0.04, is the graph of 2 to the x plus 3. So the point is these transformations apply to exponential functions as well. So we're going to see the natural base E a lot when we're working with exponentials. E is a number. It's almost like you think of E as a symbol, like the symbol pi stands for the number 3.14, right? E stands for the number, which is approximately 2.718. And where does that value come from? Well, if we were to look at this exponential expression, 1 plus 1 over n to the nth power, if we were to increase n, as n gets larger and larger and larger, and we kept plugging into this expression is going to get closer and closer and closer to 2.718281827, which we call E. So E is an irrational number, which is approximately 2.72, and it naturally occurs in a lot of models. So when we use an exponential model to model something, especially like interest, compound interest, continuous growth, this value that we're using, 1 plus 1 over n to the nth power, as n increases, it's going to get closer and closer to E. So when something's growing continuously, this value is going to approach E, and we use that as the base. So the function f of x equals e to the x is called the natural exponential function. It's called the natural base. And let me show you how to find e in the calculator, and we'll look at more equations that involve e. So look at example 4. The exponential function f of x equals 1,144 times e to the 0.0325x models the gray wolf population of the Western Great Lakes. F of x years after 1978. Project the gray wolf's population in the recovery area in 2014. So this model here, f of x equals 1,144 times e to the 0.0325 times x. This models the population as a function of time, the time or the number of years after 1978. So we want to project the gray wolf's population in this recovery area in the year 2014. So what we need to do is we need to figure out how many years after 1978 is 2014. Because that's what X represents. How many years after 1978? So if we take 2014 minus 1978, that's a difference of 36 years. So X equals 36. So we want to find F of 36, which is going to be equal to 1144 times e to the 0.0325 times 36. And let's plug that into the calculator. So let me just write that down so I can go to the other screen. Okay, so we have 1144 times e. So we have a function in the calculator that will pull up base e along with the exponent key. So you could do it all at once. So if you look above the ln key, you see e to the x. So we're going to press second and then the ln key. And you see how it pulls up e raised to, and now we can plug in what we're raising it to. So 0.0325. And we want to multiply that by 36, right? Because x was 36. And now enter. So we get about 3686, right? Because it's 3685.9. So that's about 3,686 wolves, right? Because that represents the population in the year 2014. So it's about 3,686 wolves, right, in the population in 2014. So that's what we just estimated. So that's how we use the natural base E, and we're going to see other formulas that contain the natural base E. So I had mentioned earlier that when we use formulas to calculate interest, a lot of times if it's continuous compounding in terms of calculating interest, we're going to use base E. So after T years, the balance A in an account with principal P, meaning the principal amount of money that we're starting with or investing, and annual interest rate R, remember when we work with rates, we have to put them in decimal form when we plug into a formula, is given by the following formula. So if we're looking for compound interest, that's going to compound n periods per year. We use the formula A equals P times 1 plus R over N to the N times T. So remember, 1 plus R over N to the N, as N gets bigger and bigger and bigger, that approaches base E. So what does compounding mean? That means the amount of times that we're going to calculate interest per year. So for example, we might want to calculate interest annually, which would be once a year. We might want to calculate semi-annually, which would be twice a year. We might want to compound interest quarterly. Quarter means 4 times a year. We might want to calculate interest monthly, which would be how many times a year, right? That would be 12 because there's 12 months in a year. So 12 times a year. So think of the compounding period N as how many times per year are we going to calculate interest? So let's look at this first example. A sum of $10,000 is invested at an annual rate of 1.08%. What's the balance in the account after 5 years, subject to quarterly compounding? So our money is going to be compounded quarterly, meaning every 3 months, right? 4 times a year, we're going to earn interest on, well, we're starting with 10,000, right? That's the principal amount. But every time we earn interest, our balance is going to go up a little bit. And then the next time we earn interest, we're going to earn interest on the 10,000, but plus the little bit of interest that we made last time. So you could think of compounding as earning interest on interest. Even your interest is earning money. And the rate in this case is 1.08%. But as a decimal, remember, to go from percent to decimal, you have to move the decimal back 2 places. This is going to be 0.0108 if we want to write it in decimal form. So we want to find the balance in the account after 5 years. So time is going to be 5 years, t equals 5. If we compound quarterly, so quarterly is 4 times a year. So n would be 4 in this case. So we want to use our compound interest formula. So the amount of money that we're going to have in the bank after 5 years is going to be equal to P, which is 10,000, times 1 plus the rate, R, which is 0.0108, divided by N, which is 4. And we're going to raise that to the N times T, where N is 4 and T is 5, right? We're going to do this really 20 times, right? 4 times a year for 5 years. So we're going to recalculate interest 20 times essentially. So let's plug this into the calculator. So we have 10,000 times 1 plus 0.0108 over 4 raised to the 4 times 5. So let's plug this in. So we have 10,000 times 1 plus 0.0108 divided by 4, close parentheses. Now we're going to raise that to the 4 times 5. And you can either type it in as 4 times 5, or if you want to make your life easier, just put 20, right? 4 times 5 is 20. And we end up with $10,554.08 if we round to the nearest cents. So we have $10,554.08. So that's how much money, including interest, we would have after 5 years. So we started with 10,000 and now we have $10,554.08. So I just want you to realize that 10,000 we started with, but now we have an extra $554.08. That was the additional interest that we earned at 1.08% compounded quarterly. So this amount includes the principal and the interest. So let's do another example. So now we're going to take a sum of 6,000. So the principal is 6,000, and we're going to invest it at an annual rate of 3%, which as a decimal is 0.03. And we want to find the balance in the account after 7 years. So time is equal to 7. Now we're going to do monthly compounding. So the number of times we're going to compound in a year is 12 every month, right? There's 12 months in a year. So let's plug into our compound interest formula. So A is going to be equal to 6,000 times 1 plus R, which is 0.03 over N, which is 12. And we're going to raise that to the 12, right? N times T. And T is 7. So 12 times 7. And we're going to plug that into the calculator. So we have 6,000 times 1 plus 0.03 divided by 12. And we're going to raise that to the 7 times 12, or 12 times 7, right? And 12 times 7 is just 84. So I'm just going to type that in as 84. And we get about $7,400.13 if we go 2 decimal places. So this is going to be about $7,400.13 that we would have after the 7 years if we were to compound monthly. It is possible to compound continuously, so constantly. If that was the case, then n would be really, really large, right? Because it would be an infinite amount of times a year. We couldn't even count how many times because it would be continuous. So this 1 plus r over n to the n would approach e. And that's why we have the formula p times e to the r times t. So we use that for continuous compounding. So let's look at these last 2 examples. So example 7 says a sum of 10,000 is invested at an annual rate of 1.0%. Find the balance in the account after 5 years, but now subject to continuous compounding. So it's the same scenario as above, but now continuous compounding. So anytime we want to calculate continuous compounding, we use this formula, A equals P times E to the R times T. So in this example, P is 10,000 times E to the R, which is going to be the 0.0108, and times T, which is going to be 5 years. So we're going to plug this into the calculator. So we have 10,000 times E to the 0.0108 times 5. So 10,000. Remember how I showed you to pull up E before with the exponent? So second and then the ln key. So we have E now raised to the, now we're going to type in 0.0108 times T, which is 5 in this case. So I'm going to do times 5. And we get $10,554.85. So we get $10,554.85. Now I want to compare that to the one we did up here in example 5 when we were, it was the same principle, same rate, same time, but we were compounding quarterly 4 times a year. And we got $10,554.08. Now, when we compound continuously, we're getting $10,554.85. So it's a difference of about 80 cents. We get 80 cents more. So in this case, it's slight, but I want you to realize that when we compound continuously, we're going to be earning a little bit more money. And then let's do one last example. So we're going to invest $3,500 at an annual rate of 2.73%. What's the balance in the account after 4 years? Again, if we compound continuously. So we're going to use A equals P times E to the R times T. In this case, the principal is 3,500 times E now to my rate, which when I convert it to a decimal is going to be 0.0273. And then we have to multiply that by T, which is 4 in this case, because we're doing it after 4 years. So we're going to have 3,500 times E to the 0.0273 times 4. And we could go ahead and plug that in the calculator. So we have 3,500 times E to the 0.0273 and then times 4. And we get about 3903.85. So $3,903.85. So this is going to be about $3,903.85 we would have in our account after 4 years at an interest rate of 2.73% if the interest was compounded continuously.